Today we've got the central limit theorem, and this is for bets. This is where we bet on things. So far the only bet we've made is 95% of the distribution is between plus and minus 2 standard deviations, 68% and so forth. This is what is used to make bets on averages. Like if you do an election poll, they're betting on the average. They've got some number and they've got a bet. If I'm looking at hospital expenditures and I want to know what the average hospital expenditure is, we're betting that we know the average. We don't ever know the average, but we can bet on it. And we can make the bets good or bad depending on the sample size. And all this depends on the central limit theorem. This says that no matter what distribution you start with, no matter what shape it's got, whether it's normal or upside down or anything, that when you take successive averages from samples of that distribution, those samples, the sample means, will have a normal distribution. So that no matter what we start with, we will get something that we can use for bets. Like this is an online deal, and it has a demonstration of the central limit theorem. So if I start with a flat uniform distribution and I take a sample of some size, and then I do it again, and then I do it again, then I do it again, and I do this literally thousands of times, then the distribution of the averages, this is the distribution of sample averages, will have a normal distribution with the mean equal to the population mean and the standard deviation equal to the population standard deviation divided by the square root of n, the sample size. So here, this is 2 samples, and we've done this. How many times does he do this? Oh heavens, thousands of times. And I get kind of a normal distribution shape. If I increase the sample size, I do a sample of size 9, and I get the average. Then I do another sample of size 9, and I get the average. Then I do another sample of size 9, and I get the average. And I do this again and again and again and again, and then plot the averages. Make a histogram of the averages. Then I get even more of a normal distribution when I increase the sample size. This is like if you want to find out if a coin comes up 50% heads and tails. You do it twice, you might get 2 heads, 2 tails. You do it 5 times, you might get 4 heads and 1 tail. You do it 50 times, and suddenly you've got about half on either side. So the more times, the more sample observations I have, the better the distribution of the sample means becomes normal. I'm going to bump this to 25. So this is what I started with. This is what the individuals look like. A uniform distribution, no pattern in it, but when I do sample averages, I get this shape. This is individuals. This is averages. So this is the distribution of individuals. This is the distribution of averages. Right? You always want to bet on the average rather than an individual. Insurance companies bet on the average. They don't bet on you as an individual. You buy car insurance, they look at what group you're in. They want the average bet, not betting on you. And this is why. Because if I bet on an individual, I get this whole range of things. But if I bet on averages, I get more and more and more like a normal distribution, and I can make bets using normal distribution probabilities. Right? I have no claim to anything here in the uniform distribution. It's here to there, and it's equally likely. But as I pull numbers out of there and average them, the more I take out of the sample or of the population, the more I get a normal distribution, and it becomes narrower and narrower. So this is what we use to bet. And it doesn't matter what we start with. Here's a skewed left distribution. Numbers are going to come from here more than they are from the low end. But if I take a sample of size 25 again and again and again and again, I get that shape, that normal distribution. And if I do 100 observations in each sample, it gets even better. It gets smaller and smaller. Right? The two main parts of this are, it doesn't matter what I start with. Skewed right. Normal. It doesn't matter what I start with for the population. The distribution of the averages is going to be normal. The second thing is, the more I have in a sample, the more observations I have, the better off I am. There's two problems with this. First, I need a lot of samples. If I want this, I need a whole bunch of samples. Sample of size 100. If I don't do 100, I only do 25, I get a wider spread. If I only did 9, I get a wider spread than that. The second thing is that this simulation, here we go, this is 20,000 samples of a particular size. They repeated this sample of size 9 20,000 times to get that shape. This is our bet. How many times do you get to get a sample? When they do an election poll, do they do it 20,000 times? You get one. This just astounds me. We are betting on one sample and claiming that any one sample is as good as 20,000. And that's quite a leap. But the more samples we have, the more we can rely on this bet. Get Excel going. We'll do this the easy way. We're going to do a sample of size 10 from a uniform distribution. And we need 1, 2, 3. This is just the number of samples we got. I'm going to do this the easy way. All I need is numbers 1 to 10. That's going to be my sample size. Then here, we're going to have uniform random numbers between 1 and 9. This is just a flat distribution. And to do that, we need equals rand, R-A-N-D, rand between. And between 1, comma, 9. So there's a sample from a uniform distribution, 1 to 9. Copy that formula down to the 10th spot. We got 9, 4, 8, 3, 3, whatever you've got. What happens when I average these numbers? And every time I do something here, it's going to change the sample. Every time you do something. And I'm going to calculate the average. And I'm going to cheat on this one and use the automatic command. Or you can type in equals average and mark those numbers. And here I have a new sample of size 10. It's got a 1 in it. It's got a 9 in it. What would it take for the average to be 9? I'd have to have 10 9s. I'm not going to have 10 9s. Or probably, this is where the bets come in. This is all bets. Probably I'm not going to have all 9s. Probably I'm not going to have all 9s or 1s or any particular number. I'm going to have numbers all across that range. So here I've got an average of 5.7. What's your average? 5.1, 4.4, 5.7. All those numbers are literally between 4 and 6. When we do this sample again, and if you do Shift F9, you get a new sample. And the extremes of the distribution, the 1s and the 9s, literally average out. So that I've got an average of 5.6 here. You got a new one? 5.2? 4.7. We're getting numbers in the middle. What's the average, really, of a uniform distribution from 1 to 9? What's in the middle? Add 1, add 1 and 9, divide it by 2, 5. That's the average of this uniform distribution from 1 to 9. And our numbers are about 5. Increase this to a sample of size 20. And we'll do it the hard way. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now I'm going to have a sample of size 20, and I'm going to get the same rand between 1 and 9, and then the average. Now I got 5.4. What have you got? 4.6? 4.8? 4.85? 4.6? 5.2. These are all closer together than we had with a sample of size 10. If we did a sample of size 100, the average value from those samples would probably be between 4.8 and 5.2. And you can do that pretty easily. I'm going to do 100. Cut off the bottom. All I need is 100. And I erase the average, but copy down that formula. Rand between 1 and 9. And there's my numbers. And here's the average. I get a 5.2, 5.23. If I repeat it, new randomization, I get 4.79. New randomization, I get 4.64. The more samples I have, the more I close in on that average. So this is the deal. This is what we're betting on. And I've done this now 3 times with a sample of size 100. I can do it again and again and again and again and again. 5.7, 5.4. I can't get anything bigger than 5.5 or less than 4.5. And if I did 1,000 samples, it would get even closer. This is what the central limit theorem says. It says that no matter what I start with, no matter how screwy that distribution is, when I take samples of a particular size, I will get a normal distribution of averages. And if I repeated this 20,000 times, I'd get a pretty good estimate. If I averaged those averages, I would get pretty much the population average. But each time I bump up the sample size, I get a smaller spread. This is what it comes to. The distribution of sample averages has a mean equal to the population mean, and the standard deviation is the population standard deviation divided by the square root of the sample size. If I start with a population that's got a mean of 100 and a standard deviation, I'll call it S here, of 15, and I do samples of size 20, then the distribution of the sample means will have a mean of 100. It will look normal, and the standard deviation will be 15 over the square root of 20. This is where we get back to the empirical rule. Here's the population, 100, and I go 1 standard deviation up and 1 down. This is 115. 115, close enough. And this is 85. I go up 2, that's 130, and down 2, that's 70. In this population, 95% is between 70 and 130. 68% is between 85 and 115. For the sample averages, I'm still at 100. What is 15 divided by the square root of 20? 0.35, say 3.4. Now I go one standard deviation up and one down, and I have 103.4. I go down one, I have 100 minus 3.4, which is going to be 96.6, hopefully. I go two up and two down. 95% is in here. 68% is in there. And look at the difference in the spread. The original distribution of individuals goes from there to there with a 95% bet. The distribution of the averages goes from 96.6 to 103.4 with 68% odds. Literally, I shrunk this thing from here to there. And it's normal. It doesn't matter what this one looks like. It can look like that. This one will look like a normal. So that's the way we bet on averages. I can bet that this thing here, with a sample of size 20, is going to be drastically better, smaller, narrower than the original population. And this is what we bet on. We bet on the central limit theorem. I bet that if I do a sample of size n one time, I will get a mean that will be an estimate of the population mean, which is what I wanted to know. And I will have a standard deviation that's equal to the population standard deviation divided by the square root of n. And the way these are actually written, n x bar, the average, and it's an estimate of the population average, and this S sub x bar. This is called the standard error error of the mean. This is a standard deviation of the averages. But if I call it a standard deviation, then I confuse it with the real standard deviation. So it's called the standard error of the mean. And sometimes it's written SE. These are my bets. I do one sample, size n. My sample average is going to estimate the population average, which is what I want to know. And the odds on that bet are determined by the standard error. This is called, when I come down to it, a confidence interval. And this is what a bet on the average is called, a confidence interval. I have a range and I have odds. So if I take the average and I subtract 2 standard errors, and the average, sample average plus 2 standard errors. What are the odds that the population average is going to be in that interval? This goes back to empirical rule, pure normal distribution. Here it is, x bar plus 2 standard errors minus 2 standard errors. And this is the way I write it because that's the way I learned to do it. Write it, call it SE, if that helps. It certainly saves writing. But what are the odds now? Right back to the normal distribution. What are the odds that the true population average is in that interval? Plus and minus 1, plus and minus 2. This is right back to the old days. 95%. That's called a 95% confidence interval. And that's my bet on the average. Everything I do, I'm making a bet on the average. What if I wanted a 68% confidence interval? 1 up, 1 down. Exactly. And the empirical rule only deals with 2 and 1, 95 and 68. I can have any probability I want. I just have to look up how many standard errors I need to go up and down. And I'm back to the normal distribution. And if I want 80% confidence interval, what does an 80% confidence interval look like? In this one, how much is in the middle? 95. 2.5 out on either end. If I have an 80% interval, it's in the middle. How much is on either end, outside of the interval? 20 altogether, 10 on each side. So if I have an 80% bet, what's the chance that the true average is less than that? 10%. Up here, 10%. I can choose which of these I want, except what's the difference between this and this? We can look it up. Get on the normal distribution in Excel. This is where I have to use the normal distribution function, and everything comes from the left. So if I want the low end of this 80%, I want this. This is going to tell me how many standard errors it is. I need equals norm dot s dot inv. And this is going to tell me what the multiplier is for the standard errors. I put in 0.1, 10%, and it is minus 1.3 standard errors down. What if I want the upper end? I want this. The only way I can get it is to come from here up to there. So how much is from there to there? 90%. So instead of that, I use equals norm.s.inv 0.9, and what do I get? Same thing. One's negative, one's positive. So for an 80% confidence interval, this would be 1.3 times the standard error down and 1.3 times the standard error up. This one, 95%, is minus 2 and plus 2. This one is minus 1.3 standard errors and plus 1.3 standard errors. What's the difference between 95 and 80% bet? What changed between those two? Did the average change? Did the standard error change? All I did was change how far out I went. And this is a problem that it's hard to explain to someone. I used to do this for timber companies for the most part. How much wood do you have? You've got 20,000 acres of land with trees on it. How many cubic feet, many pounds, how many board feet, whatever the units are, do you have on this? And the answer is a confidence interval. So I would say, what do you want? You want to be 95% sure? Or 80% sure? Or 68% sure? Anything. What would they say they wanted? 95. Always. Because it sounds good. But the difference between this and this is how many standard errors I went up and down. You ever see Father Ted? Well, it's an English thing, and it had the guy who played House. And Father Ted was a little slow. And they were looking out, and they're in England, they're in the middle of nowhere, and they've been basically banished from the big city. So they're out in the country, and all that's out in the country is sheep. Father Ted is looking out at these sheep, and he says, "Those sheep aren't very big. They're only this tall." And the guy tries to explain to him, if you go closer, they will be bigger. True? That's what these things are. This is purely, where do I choose to stand to look at this thing? This is how and why we can estimate an average. And people always choose the 95% confidence interval. It sounds good. Boy, I'm 95% sure. Well, at the same time, you're 80% sure on a little different width. I'm 50% sure on another width. It depends on how far I stand back from the sheep. The sheep are the same size. If I stand way back here, I'm looking at 95%. If I move closer, I get to 68%. I get to 50%. All of these things are the same, except I'm looking at them from a different perspective. Right, there's one more thing here. The standard error is the standard deviation divided by the square root of n. The bigger n is, the better my estimates are. Why don't I make n huge? Suppose you went out to the parking lot and what you wanted to estimate was the number of wheels on vehicles of any sort. See any bicycles outside? Motorcycle? Cars. How many wheels has a car got? 4. Here I am, I'm counting wheels, and I can do that pretty quickly. So if I want to estimate the average number of wheels on a car or a vehicle, I can count all day long. I can get a sample size of 1,000 in no time. What if I want a sample size of 2,000? That's better. Is it twice as good? This is what I have. I've got sigma, a standard deviation, divided by the square root of n. Here's n. What's the square root of 1? 1. So if I'm here at 1 sample, it's 1. What's the square root of 16? 16. What's 1 over the square root of 16? This is what I've got, divided by the square root of the sample size. 1 over 4? 1/4, 0.25. That's there. What's if I have a sample of size 100? What's 1 over the square root of 100? Square root of 100 is 10. That's out here. This is 0.1. This is what the sample size gain looks like. If I do twice as many samples, I don't get twice the gain, because as I collect samples, the value goes down by the square root, not by the divisor. As I do this, I get less and less gain with each additional sample. What happens to the cost? How long does it take you to count how many wheels a car has got or a vehicle's got? You can do that pretty quick, can't you? But you've got to go and look. Then you've got to go and look. Then you've got to go and look. What's the cost of continuing to look? Is there any difference between the cost of counting wheels on the first car or vehicle or the 100th? Takes you as long. The cost looks like a flat line. The cost doesn't change, but the gain changes. It goes down. So the cost is fixed at best. We used to send people out in the woods. They would wander around the woods, measure trees. Put one person out in the woods to measure trees. They got to go from here, measure some trees. They walk somewhere else, measure some trees. Walk somewhere else, measure some trees. It takes them the same amount of time to measure those trees at each time. But they have to walk between them. What if we have to go to a second day? What if you have to stay and count wheels on a second day? What do you have to do? You need more time. You've got to go find a motel room somewhere and drive there, drive back. So the second day, the cost of each sample is even higher. And you're getting less and less and less. What this comes to, and this is something that is kind of amazing, I have seen people do samples with a sample size of 20,000. What was the gain from 19,000 to 20,000? Where are we on this curve? Where's 19,000? Way over here. How different is 19,000 from 20,000? This gets closer and closer and closer to zero as I go along. In fact, in statistics, a sample size of 30 is considered large. And if you look at the normal distribution, and standard deviation and cost and standard error, by the time you get to 30, you have got everything you're going to get. Anything you get past 30 gets you a little bit more, and a little bit more, and a little bit more, and each time you get less and less and less. And the cost is at least fixed, if not going up. This is like doing a leprechaun sample. This is, you know how tall leprechauns are? There's an official rule for how tall leprechauns are. There's a height limit for leprechauns. If they're taller than that, they aren't leprechauns. So you've got to do a leprechaun sample. What happens? You send people out to measure leprechauns. You've got to catch a leprechaun to measure the height. What happens when you catch a leprechaun? Gold. You get a pot of gold, right? So I send people out to measure leprechauns. They find one, they catch it. After all the training, it takes a long time to learn to catch leprechauns. Otherwise, everybody'd be doing it. But now this person I've trained and spent so much money on has got a leprechaun, measured the height. They got a pot of gold. Are they coming back? Then I got to go get more people and train them to catch leprechauns. And every time I do this, I incur a tremendous expense. And as soon as I catch a leprechaun, they're gone. Gathering samples is expensive, and I have to analyze the results. I can do it much faster now than I could before, but it doesn't happen immediately. Everything about statistics is working against you. The more samples you have, the better off your estimates are. I want to be way out here. But by the time I get there, each additional one is almost worthless. And the cost has gone up, if anything. Every day I have to keep somebody in the field costs more. There's a fixed cost. You got to keep them there. You got to get them there. Then you got to do it the next day. And it costs more. Anything beyond 30, basically, is entertainment in statistics. And I have seen people do samples of size 2,000. And I said, you don't need 2,000. And they insisted on 2,000 because that's what they thought they were supposed to have. I said, I can get you the same answer, or almost as good, for a third of that. What do they say? No way. You can't do that. Well, I can, and I did, and I often take advantage of it. You want 2,000? No problem. I'm happy to help. This is like you want to go buy a car, and the car costs $40,000, and you insist on paying $60,000. Are they going to fight you? You got 60 grand? You're my friend. This is all of statistics. This is all the estimation part in one graph. More samples are better, but each one gets me less and less. The cost is going up, if nothing else, and it's all because the central limit theorem says that if I divide by the square root of the sample size, I get better and better estimates. And the whole deal with setting sample size is, where does the cost no longer justify the gain that I get from an additional sample?